Hi, my name is Sean Kavanagh and I'm a PhD student in the groups of David Scanlon at University College London and Aaron Walsh at Imperial College London. And my research uses modelling techniques to understand and optimise solid-state solar photovoltaic materials, looking at bulk properties as well as more material-specific behaviour such as defects and disorder. Today, I'm going to speak about some of our recent work looking at the dynamic behavior and impact of point defects, specifically focused on cadmium telluride, which is a highly studied and technologically relevant solar cell material. To give some of the context behind this work, as I'm sure many of us are aware, when defects are created in the bulk material, we get atomic relaxations of the neighboring atoms in response to the dangling bonds and lattice disruption introduced by the defect, with these distortions depending, for example, on the charge state or the electronic occupation of the defect site. However, due to the potential complexity and high dimensionality of the structural potential energy surface, often we can have multiple local minima or locally stable structures for a given defect. For example, here I show the calculated potential energy surface of the neutral cadmium vacancy in cadmium telluride, where we find three distinct local minima corresponding to different potential low energy defect structures. There's actually a fourth possible state here, as this bipolaron state on the right here can have the two whole polarons either spin aligned or spin anti-aligned with a small energy difference between these. So I imagine that this diagram on the right looks familiar to most here, but for those who aren't familiar, essentially it's the way that we analyze the thermodynamics of point defects in semiconductors within the field of computational defect modeling. They're called defect transition level diagrams or formation energy diagrams, and they plot the formation energies of defects in their various charge states against the Fermi level in the material, relative to the valence band maximum, which is set to 0 eV here. Normally, we just show the lowest energy, i.e. the most favorable charge state for each value of the Fermi level, which would correspond to just the saturated color lines here. And this simplifies the analysis and the diagram when considering a broad range of defects at once. Looking closely at this defect energy level diagram, we see that the charge transition level position, which is the Fermi level where the equilibrium charge state of the defect changes, i.e. from neutral to -2 here, that this position, which is essentially one of the main results we take from these plots, changes drastically depending on the structure you find for the neutral vacancy, from having two shallow transition levels near the valence band maximum from 0 to -1 and -1 to -2, to now, in fact, having a single deep negative U level around 0.4 electron volts above the VBM. By negative U, we mean a double acceptor level where the equilibrium charge state jumps directly from neutral to -2, and so the singly charged -1 state is always unfavorable and would rather disproportionate into neutral and -2. The majority of previous theoretical studies had suggested that the tetrahedral structure was the cadmium vacancy ground state arrangement, missing out on this true ground state, the tellurium dimer structure that we find here. Again, this being due to the local minimum of the tetrahedral structure being closer to the unperturbed host crystal structure on the potential energy surface. And as we can see here, this can drastically affect the thermodynamic and electronic behavior of defects. So in fact, this is a general issue in computational defect studies where ground state configurations can sometimes be missed as our local gradient-based structure optimizers get stuck in these local minima, missing out on the true global minimum or ground state. I've been supervising a talented master's turned PhD student on a project looking at tackling this issue, and we've some truly exciting results that are currently being written up, so we hope to be able to share those soon. So these observations led us to question, with the presence of metastable states like this on the potential energy surface for defects, how important can the structural dynamics and potential transitions between these defect structures be for device performance? Well, in our work on cadmium vacancies, we found that the presence of these low energy metastable bipolar ion structures can actually enhance the overall recombination rate, as it was easier for the -1 charged vacancy to capture a hole and then transform to this transient species before relaxing down to the dimer ground state and then capturing an electron to complete this recombination cycle. In fact, in recent years, there have been a couple of papers from big names in the field which have reported similar behavior, finding it to explain experimental observations which had previously been in disagreement with theoretical predictions. And I show on the left here a few select examples of this. And so in this project, we wanted to step back and think about the potential pathways by which such defect dynamics could affect their behavior. If we think about this in terms of potential energy surfaces, where we have energy as our y-axis and Q, our structural coordinate, as the x-axis, we see that there are a couple of possibilities. We could have this case of degenerate minima, in which there exists several energy equivalent arrangements of the defect. And so at room temperature, we might expect a certain amount of hopping between these structures, depending, of course, on the height of this energy barrier between them. While this is unlikely to significantly affect the recombination behavior, it is important in the context of comparisons between theoretical and experimental measurements of defect structures, as depending on the experiment temperature and timescale, the defect may appear more localized and anisotropic than is truly the case under operating conditions. For example, electron paramagnetic resonance measurements, which can give really detailed characterization of point defects, are typically performed at near 0 Kelvin temperatures, and so would be likely to only show the symmetry broken anisotropic defect states. Whereas under room temperature operating conditions, such as DLTS, for example, the defect may be hopping between equivalent structures much faster than the experimental timescale, behaving effectively as an isotropic species. Another possibility is that we could have fast charge capture into a metastable arrangement, which can then undergo some form of internal conversion to the ground state, again with a rate depending on the energy barrier, and then we could have slow or fast capture out of this state. So this extra step here could act to either catalyze or impede the overall recombination cycle. And this is the case that is featured in the papers shown on the previous slide and in our work on the cadmium vacancy. However, another possibility is that you could start from the ground state arrangement, and then if you have a low-lying metastable state with a relatively low kinetic barrier, you would end up with a certain thermal population within this metastable state. If this then has a fast capture route, this could potentially catalyze our recombination cycle as well. The final case to mention is the potential for photoexcitation from the defect ground state to the metastable state, which could certainly occur under standard operating conditions for solar cell materials, where we have an ample supply of photons in the material, with this now depending on other properties such as the photoionization cross-section or transition dipole moment between these states. To think about the recombination process as a whole and the potential pathways that these metastable states could introduce, it's instructive to look at it using a graph network. The main requirements for electron hole recombination are that, one, we establish a closed path, which eventually brings us back to the initial state, and that we have both electron and hole capture occurring, which here means essentially visiting the bottom half of this graph and at some point returning to the top half. Here, the dashed arrows represent charge capture processes, while the solid black arrows represent an internal conversion reaction, i.e. a charge conserving transition between the ground and metastable defect structures. So here we consider the case where there is one accessible metastable arrangement for the two defect charge states, so labeled by Q and Q plus or minus 1. And we see that there are a couple of potential recombination paths in this case. Firstly, you could have a simple charge capture to the Q plus or minus 1 state and then charge capture back. And so this corresponds to our typical Shockley-Reed-Hall recombination process. In C, you see that we could have a charge capture into a metastable state, which then relaxes down to the ground state, and then charge capture back to our initial state. And this corresponds to the process or behavior which has been reported in those papers I showed previously and in our work on the cadmium vacancy. However, you could also have these processes shown in D and E, where you have initially an internal excitation to the metastable state before charge capture to the Q plus or minus 1 state and charge capture back to our initial state. Thinking about the trends in capture rates that we might expect for these metastable defects, it helps to visualize their charge transition levels on the defect formation energy diagram introduced earlier. By having a higher energy, the metastable state will cause the movement of the charge transition level position such that it will be closer to the band edge corresponding to capture into the metastable state. So this can be a little tricky to get your head around at first, but it helps to think of it diagrammatically as shown here. So for example, for the 0 to -1 charge transition, if the energy of the -1 state increases, corresponding to, say, a metastable arrangement for the -1 state, this will push our transition level closer to the conduction band minimum. And so the 0 to -1 transition level is now closer to the conduction band minimum, where we would be capturing electrons to transition from our neutral state to the metastable -1 state. The same logic applies for going, say, from the neutral to the +1 state, where we are now closer to the valence band maximum when capturing into this metastable +1 defect. We can also think about this in terms of positions on the vertical energy level diagram as shown on the right. And this behavior yields some general implications about the likely rates of charge capture at transition levels involving metastable states. So conventionally, it has been taken that charge transition levels close to a band edge will yield fast capture of that charge carrier. So for example, fast electron capture for levels near the conduction band minimum, but slow capture for the carrier from the far edge, so for hole capture. This is the conventional rationale behind deep defect levels near the mid-gap region being the most likely to be efficient recombination centers by balancing moderate hole capture and moderate electron capture to yield overall fast recombination. So while this conventional wisdom does hold in many cases, particularly for defects in conventional semiconductors and ionic materials like oxides, where the defects themselves are high symmetry, exhibit harmonic potential energy surfaces, and don't distort much between different charge states. This behavior often does not hold, however, for many emerging inorganic materials which exhibit anharmonicity and significant structural distortion between defect charge states. Another implication of this movement of the charge transition level is that the metastable structure must not lie too high in energy if it is to affect recombination. Otherwise, this charge transition level will actually end up outside the band gap region and will be energetically prevented from capturing charge carriers. In this way, the original separation of the charge transition level and the band edge kind of sets our energy window within which the metastable structure must lie if it is to affect recombination. So in combination, these trends suggest that if low energy metastable states exist for a defect species, it is likely that charge capture into this defect state could occur faster than for the ground state arrangement, explaining to some degree the recent observations mentioned in the literature and highlighting the potential importance of metastable defects in these processes. In our study of defects in cadmium telluride, we found that the tellurium interstitial was actually an interesting exemplar of this behavior, and so we chose it as a case study for this project. Tellurium interstitials have low energy metastable states for both the neutral and the +1 states. So in the ground state arrangement, tellurium interstitials adopt this split interstitial dimer arrangement, directed along the 110 direction in the +1 state and then slightly twisted about this axis in the neutral state. For the metastable states, it's essentially a bit more complicated. We have a C2V type arrangement for the neutral state, which then distorts to a CS point group symmetry for the +1 state. And these metastable states actually represent the intermediate structures in the diffusion mechanism of tellurium interstitials in cadmium telluride. Visualizing on our friend the defect formation energy diagram, we see that the combination of these 4 defect states results in 4 potential charge transition levels. The close spacing of these levels on the diagram here is a result of the fact that the metastable states are only slightly higher in energy than the ground states in both cases, being 36 millielectron volts higher for the +1 state and 120 millielectron volts higher for the neutral state. We also note that these levels are all closer to the valence band maximum than the conduction band minimum here, which from our conventional wisdom mentioned before would suggest that hole capture rather than electron capture will be the dominant process or faster process here. So there's a lot going on with these diagrams, so I'm going to do my best to briefly explain what they show. To analyze the electron hole recombination kinetics at defects, we first map out these potential energy surfaces between the defect in its different charge states. So for example, here going from neutral in the upper orange to -1 in the blue potential energy surface. From these potential energy surfaces, we can determine the classical energy barrier to the charge capture transition, which is represented by the delta E's here in these diagrams, as well as solving the one-dimensional Schrodinger equation to obtain the effective vibrational frequencies and calculating the electron-phonon coupling, all of which contribute to our final charge carrier capture rate. For the most part, the overall capture rate is primarily governed by this transition energy barrier, behaving essentially like an activated process with large energy barriers yielding slow charge capture and vice versa. Here, transitioning from the upper orange to the middle blue potential energy surfaces represents hole capture by the defect, so going from neutral to +1, while from the middle blue to the lower orange represents electron capture, so from +1 back to neutral. As expected from the transition level positions in the band gap, in pretty much all cases, we find fast hole capture with small capture barriers and close overlap of the shaded vibrational states and going from the top orange to the blue potential energy surface. For electron capture, however, so transitioning from the blue potential energy surface to the low orange potential energy surface, we see that there are no low energy crossing points for A and B, which involve the ground state arrangements for the +1 interstitial. It is only when the metastable arrangement for the +1 interstitial is involved, as in C and D, that we find significant potential energy surface overlap and a tractable energy barrier such that electron capture now becomes possible. This is then clearly demonstrated by our calculated capture cross sections, which quantify the rate of charge capture by the various defect levels. We see our high hole capture cross sections for each potential transition, but a massive 7 orders of magnitude difference in the electron capture rates represented by sigma n once the positive interstitial, the metastable state for the positive interstitial becomes involved. The result of these calculated kinetics is shown schematically here. And by now facilitating a moderate rate of electron capture, the metastable structure for the positive tellurium interstitial transforms this defect species from being a benign defect center, which is only capable of capturing holes and not electrons and thus unable to contribute to recombination, to now actually being an important trap level in this material. By virtue of its low energy relative to the ground state and a low energy barrier to the structural transition of 0.08 electron volts calculated using the nudged elastic band method, we have significant thermal excitation of the positive interstitial to the metastable state at room temperature, which can then capture electrons and transform to either the ground or metastable structure of the neutral state. While the earlier studies I showed looked at similar behavior involving capture into a metastable structure before relaxing and then capturing back to the initial state, this process actually involves thermal excitation to a metastable structure before capture and has not been previously reported to the best of our knowledge. The main conclusions from this work are that the dynamic behavior of point defects can be crucial for understanding their impact on device performance, demonstrated here with a case study on tellurium interstitials in cadmium telluride. We pose that metastable defect structures could actually be much more important to non-radiative recombination than currently thought, particularly in the case of emerging ionic covalent materials multinary compositions and/or highly mobile defects like tellurium interstitials, where anharmonicity and soft potential energy surfaces are likely to give rise to many low-lying, easily accessible metastable structures, enabling this behavior reported here. I should mention this project actually came about after I received a travel award from the Max Planck Research Institute in Germany to visit the lab of Dr. Christoph Freysold. We thought these findings would be particularly suited to being discussed in the emerging PV community, and so we decided to submit this for the upcoming Faraday discussions on emerging inorganic PV materials, where the work will be discussed openly and any relevant comments or discussion are included in the final version of the paper. To end, I'd like to thank my mentors, Aaron Walsh and David Scanlon, the Max Planck Institute for organising the Coffee with Max Planck Award, and finally, you all for listening.